All right, in this video we'll talk about conditional probability and the general multiplication rule. So conditional probability, we use the notation A given B. So this bar down the middle means given. So the way that we understand this is when I say that A given B, I mean that B has definitely happened, so there's no chance involved with this. And so knowing that B has happened, what is the probability that A will happen? So to give an example, we're going to roll a die. Here's my trusty red die, and we know that the sample space for that is 1, 2, 3, 4, 5, and 6. And let's define event A to be that you would have an even roll, and event B that you would have a 1, 2, or a 3. So in a Venn diagram, what this looks like, so here's my entire sample space. I have two events A and B. Here's A and here's B. A has the events 2, 4, and 6, and B has the event 1, or outcomes 1, 2, and 3. Now notice they have the 2 in common. So when I say A given B, I'm actually narrowing the pool of possible outcomes from the entire sample space down to just this subset of B. So the outcome is definitely within the set B in this event. So it's a 1, 2, or 3. So now I want to know what are the odds, or not odds, what's the probability that I have an even outcome, knowing that the outcome is from this collection of B. Well, there's only one even number in B, and it's the event here in the overlap. And so the probability of A given B in this case, I know, is 1 out of 3. There were 3 possibilities in B, but only one of them was even. So this kind of gives us an idea of how we might have a rule or a way to compute, just more generally, a conditional probability. And in fact, the formula that we use here for the probability, now I'm going to say just generically, E given F, is the probability of E and F. So that would be the overlap, things they have in common, divided by the probability of F. So the E and F, this overlap area, that is, whatever here is in the overlap. So that's that probability. And so in the earlier example, what I was doing is I was removing all these options and focusing just on B, and then looking at this part of B, and so this was A and B, and I'm looking at this piece relative to this whole, and so that's what we're seeing here in this formula. Let me give you another example. Let's say that you have a population maybe of 1,000 students, and we know that maybe 600 identify as female, and maybe we have 300 that are STEM majors, and certainly there's some overlap. Let's say that 200 are there are female STEM majors, so there are female and STEM. So we're going to call this event F, and we're going to call this event E. So engineering right there. So this would be F and E. So let's look at a Venn diagram. Here's my sample space. There are 1,000 students, and I have 600 of these students who are female, so this is F. There's some overlap with these science, technology, engineering, and math majors. of which there are 300. For the female STEM majors, there are 200 in this overlap. All right, so let's talk about some of the conditional probabilities that we can construct using this information. What if we want to know the probability that you would select a female student given that you have selected a STEM major? Well, knowing that we've narrowed our options down to STEM majors, the pool from which I can choose has been narrowed from 1,000 down to just 300. Now, once I narrow the pool down to just these 300, so nothing else exists out here, so this goes away as far as the possibilities. So I have 300 from which to choose. Now, what's the likelihood that I will choose a STEM major? Well, included in this 300 are 200 STEM majors. So there's a 200 out of 300 chance, which reduces down to 2/3. Now, I want to point out, if we reverse the order, engineering given female, that this changes. There were 600 students who were female, and so now we're talking about this is our new pool. There were 600. Of those 600, 200 now are engineering. So this is 2 out of 6, or 1/3. So I want to add something to our way of calculating. So here I said that this was a probability. Notice in practice, sometimes I'm actually using a count. So we could also write this as the count of elements in E and F over the count of elements that are just in F. And E and F are arbitrary, so if you reverse the order, it would just change the denominator. So if I said F given E, there would be an E in the denominator here. Okay, so let's go to the general multiplication rule. So I've defined the probability of E given F as the probability of E and F over the probability of F. So in this next, what I'll call rule of probability, I'm basically just going to rewrite this by multiplying both sides by the probability of F. So that will clear this fraction, and I'll be left with the probability of E and F equals the probability of E given F times the probability of F. And this is called the general multiplication rule. Alright, and lastly in this video I want to say something about independence. So two events, E and F, are independent if the probability of E given F equals the probability of E. In other words, this means knowing that F has happened does not affect the probability of E. So this provides no additional information. The probability that E will happen, knowing that F is just the same as the probability that E would happen just generally. So that means independent. Now, if these two things are not equal, so if the probability of E given F does not equal the probability of E, then we say E and F are dependent. So in the next video, I'll actually pull all of this together with some examples. I hope you'll join me.